that's the kind of summoning power I have. Last time these are the same notes as the last lecture, because I slowed down a bit because some of you wrote that I went a bit quickly. And since I've got a few lectures to spare, I can dial it back somewhat. So we're now across lectures. So this is still lecture 16, which is why you haven't got any new notes. And we are about 2/3 of the way through. In fact, we were just about on summing amplifier. If you haven't got the notes with you, it really doesn't matter. But in the first half of this lecture, which we did last time, we talked about inverting amplifiers, non-inverting amplifiers, and we talked about the unity gain buffer. And we worried about things like input resistance and output resistance and gain. And we said we were interested in all this because the operation amplifier is an analog building block, in the sense that you can just buy it, put a few resistors around it, and it will do something mathematical for you, like addition, subtraction, multiplication, logarithm, that sort of thing. And you don't have to worry about how the... Come on, I start. You don't have to worry about how the transistors inside a BIOS, or you don't have to do any difficult, or in quotes difficult, calculations. You just have to know how to derive a few formula, and you get gain is some resistor divided by some other resistor, with or without a minus sign. So we got through the one input, one output ones, such as the unity gain buffer and the inverting one and the non-inverting one. And can't you change it to the drop sound? Because I can do quite a good copy of that drop sound. And if I do it on the train, people look around and it thrills me. Often I'm alone on the train, I must admit. Anyway, so if you have more than one input and still one output, you could add up voltages if you wanted to, or subtract them, or that sort of thing. And the circuit that we use for adding or for adding them up is a summing amplifier. And of course, if one of your voltages was positive and the other was negative, you'd end up subtracting them because the algebra would still apply. But we call it a summing amplifier anyway. You could have mentioned it. Ah, for the love of God. Right. Well, I'm not stopping now. Who's not got lecture 16 notes? Fine. I blame you all for this. I have to dial Batman now. Commissioner Gordon. What theatre are we in? Cheers. It turns out computer says no. Never mind. We'll carry on sort of as we can. Because there isn't a lecture's worth of material there, there's only about 10 minutes, and the rest of the lecture is designed to be a bit of a sandpit, I suppose, so we'll do that first. Then we just blank the projector. So, as far as the op-amp circuits go, we've got this one. You don't have to make notes on this, it's all in your slides and whatever. And with this one. So what's this one? Inverting. Catch? And the packet's quite open, so you have to be careful now. Oh. Doesn't matter. I could try it with beer as well, but it wouldn't be as successful. So this one's inverting, so by process of elimination this one must be... Right, okay. You better pass them down. So, what's special about this one that isn't special about that one? Tell me something about this circuit.
Yeah, it's a virtual earth.
It does have a virtual earth. We haven't agreed this in advance. So how does the virtual earth work?
It's almost like a ground.
Yes.
It's nearly zero.
Now that's what is the virtual earth. How does it come into being? What is it about the op-amp that causes that situation to exist?
The gain is infinite.
Yep.
Yeah, so the input has to be equal, almost equal to each other.
Yep.
Yeah.
And therefore, when you've done the half bit, there's only one thing left.
That should now be out to 0.
Yeah, okay. The one, look, what's one of the inputs at?
0.
So the other one?
Should be at 0.
There we go. Pass him the biscuits. So the virtual earth exists, just in case you didn't hear that. Did you have that as well? Or are you shaking your fist at something else?
I was congratulating you.
Ah, right. Well, you have been congratulated from the back. So we had a click of like somewhere, I would assume. So yes, these, while the op-amp gain is infinite, which I didn't really specify, but there we go. The op-amp will force its two inputs together, and if I ground one of those, that means the other one must be grounded as well. Why is it a virtual earth, and how does it exist, and how is it sustained? You will find that in past exam papers as a question. So to be able to write a sentence or two that says that logic is what's required. I'm not saying if it's this year's or not, but it has happened in the past. So what about the gain of this circuit? How would we work it out? Then tell me what it is. How do we go about working out? What's the first step? Anybody? Go ahead.
Sum the currents at the inverting node.
Sum the currents at the inverting node. Let's have a different colour of chalk. Just for a minute, I thought you were the AV man. There's a tutorial sheet floating around as well, somewhere. There's a new tutorial sheet, problem sheet, new problem sheet floating around somewhere. So we need some currents. We'll have one here, and one there. And we'll call this one IF, and we'll call this one I, for in. So if I was to sum the currents, who did that? We'll have to go upwards. Which means I have to be very tall. So if I'm summing these three, this arrow is that way. So what shall I write first? Is it to minus IF? Why is that? Yes. Just in case you didn't catch that, there is no current flowing into this bit here. No current flowing into the op-amp's input because we're assuming infinite input impedance. And that assumption is entirely compatible with the got infinite gain assumption that we're making as well. So if there's no current in there, this current and this current must add up to each other. So if you were to put them on an equal sign, either side of an equal sign, one would have to be equal to minus the other one. So we'd have to say I in, or II, is equal to minus IF. Is that big enough, or do you want it bigger? Big enough. Right, okay. So what's the next move? I think you need a biscuit. Where do they go? Oh, right, okay. How's your... to get it to go straight, it has to spin. It makes the air... Yeah, let's do some fluid dynamics. It'll be great. So what's the next move then?
Change the currents to what I represent the first 5 more.
Yes, represent. We're going to send them down that way. So we'll have to do... That's not quite enough for a biscuit. What shall I write? If this is my circuit, what shall I write?
for the VI,
Yep.
it's VI over
Why? It is, but you've gone and done something else as well. You've got rid of something which is 0.
the voltage at that.
Yes. It's quite important that you worry about it for a bit, because when you have to do it without the assumption that the gain is infinite, if you just write 0 there, what you've done is implicitly assume the gain's infinite, and when it comes to the bit of the analysis where you work out what the gain dependence is, you'll be sat there going, how do I proceed? Because there won't be a space in your equations for AV. So it's, even though you are right, we write V in minus 0, because this is at 0, because what we're really saying is that this is V minus and V minus equals V plus, because AV is infinite, and therefore V minus equals 0. That's an equals. That's the logic that's involved in making that 0, and that's the mathematical expression of what you said earlier with regard to how is the virtual ground sustained. I can leave that, actually no, I can't really leave that, but I'll try. So that represents V minus, and we've got to divide through by Ri to give us a current, because we'll have volts over amps, which is ohms. And that's all equal to minus from there, and we have to do IF, so we'll do, what will we do?
V naught minus naught
Yeah, over RF. So we'll do, what we're really saying is what's the voltage across there, and what's the voltage across there, and then divide through by Ri to make on, and RF to give you the currents. So we'd have V out minus 0 over RF. And if you can get this line, the rest is just algebra. There is no electronics involved. It's the making certain of this minus sign, or if you've drawn your currents differently, there might not be a minus sign there, it could appear somewhere else. But the making certain of this expression is the key point. After that, if you sod it up, it doesn't really matter, because I'll be able to see where you did it. But if you don't get that, what you're really saying is, oh, I didn't understand this, sorry. So this is the important bit. I don't give a damn about the rest. If you did want to deal with it, you'd get rid of the zeros, so you'd have VI over Ri is equal to minus V out over RF, and then you'd multiply through by Rin and RF. I'll go over here to give you VI RF is equal to minus V out Rin, and then you would divide this side by V in to leave you with minus V out over V in Ri is equal to RF, and then you divide through by Rin to leave yourself with Rin, and then you multiply through by minus 1, and that would be it. That's the gain for that circuit, and it's the same as in your notes. So the maths bit I'm not too worried about. That's just practice. Happy? Right then. What's the time? Right, if I could see the clock, I'd know. What?
20 past 11.
Right, okay. Because if Batman doesn't show up, I still have to talk about multiple input circuits, otherwise you won't hear about them at all. So, let's carry on with this one for a bit. And I'll get a new bit of chalk. Nice big bit. There we go. So it's the same circuit. But now the gain is not infinite. What's the first move? Yes. You're doing well out of me, aren't you, biscuits wise? So we've got some input current I in and some feedback current IF. This resistor is the feedback resistor, which is why I called it sub F. So if we sum the currents, I am, yes. Always please. I just carried on old-fashioned.
Okay, yeah.
If you work it out, tell me what it is. So I know. That do you? Enough. It'll pop up these planes at the minute.
Yeah.
So you'd sum the currents into the inverting node, not the minus node. There is secretly another plus and minus, which I'll talk about in a bit. So if we did that, what would we end up with? On someone other than you, you're still eating.
AI equals minus IF.
Yes. In is equal to minus IF. So nothing's changed yet. What will I write next then?
Doesn't write the same thing like voltages, resistances, bring them up.
Yeah.
Voltage, like you don't know.
Yep.
AB or
Righto.
V minus.
Does anybody else want to finish that? Because what will happen is I'll get a load of exam scripts back to Mark, and there'll be one that's got biscuit crumbs down the lining, and then I'll know whose it is. So, someone from over here maybe. Don't make eye contact, don't make eye contact. I don't want to do it. Come on. Feel a rush of adrenaline. Yep.
That would be the same as the beginning few steps. So I will be VI minus V inverting over RI,
Yep.
which equals minus V out minus V inverting over RF.
Yes. The important thing is that we didn't say V minus is equal to 0 automatically, because we can't in this one. So, you better throw in the biscuits. We have VI minus V minus upon RI is equal to minus V out minus V minus upon RF. And we can't say this is 0. Ooh, hello. I thought just for a minute I thought the colour had changed. Yeah, right. So what we have to do now then is figure out some way of getting rid of the V minuses. And you might want to be tempted to eliminate them from this expression, but you can't. What you must do now is get V minus equals stuff and things. And then you put that equation for V minus equals stuff and things into the op-amp equation. And that, along with V plus, which is 0, and that will give you V out is equal to a load of stuff in terms of V in and resistances, because you've substituted out the V pluses and the V minuses. So, I'd have to have, anyone want to do that for me? I don't trust you anyway. We'll cross multiply and we'll have V in Ri is equal minus V minus R. Oh, I made a mistake already. RF is equal to minus V L Ri minus V minus Ri. Happy? That's multiplied through by R and Ri and RF. So then we'll get all the V minuses together. So we'll do minus V minus RF. Plus V minus Ri is equal to minus VI RF minus VO RI. And then we'll put a bracket around this lot and we'll end up with V minus RI minus RF. Have I made a mistake?
Yeah.
What?
That should be plus.
Where should be plus?
The
VOR.
V.
This one?
No, the other one. The one beside it.
The one at the end of the second line.
This one?
Yeah.
Down.
Thought so. Down. This one?
Yeah.
Thought it should. Because in my head there's a plus there. And I'm still wondering where that's gone. But we might track it down later if we're lucky. So what does that mean? Is
Well, it should be the other one.
It's not.
what?
Because you've kept the sides the same, so you've just plus the V. Yeah. Plus the V.
Hang on.
Oh,
I can think of a better way of dealing with this. Let's try again. Right then, so V in Ri minus RF, god damn it. V minus. It's difficult if you've done something once, you think, no, that's wrong, I'm going to rederive it. And what you'll do is the little bit of memory that remembers. You'll remember the mistake you just made, and then you'll rederive it with the mistake in it again, and you'll be very frustrated by that point. So you have to be quite careful, watching out for whatever was wrong. So this is multiplied through by that, is equal to minus, it's a minus around the whole thing, isn't it?
Yeah.
Nah. There we go, beating it. So it's minus V out Ri plus V minus Ri. Happy?
Yeah.
Happy or not happy? Should we have a quick vote? Who thinks I'm good? Who isn't sure? The rest? Nobody. Right. So then we'd say, we'll collect up all the V minuses, so we'll have minus V minus RF, so this one, minus that one because we take over the other side, equals minus V out R in, so we've done that one and that one, so there's only that one to go, and that has to become minus because it's taken over. If you don't like the idea of taking things over and negating them, you can say I'll just add or subtract both from each side, and that will do the same thing. So I got my minus, which is what I was hoping for. So I'll put brackets around the V minus bit, so we'll do V minus brackets minus RF plus minus minus RI is equal to minus V out RI minus V in RF. And then that's an equal sign. Hang on a minute. So then we'll divide this lot by the brackets, leave V minus equals something. So we'll do V minus is equal to minus V out RI minus V in RF divided by minus RF minus RF minus RI. So this is where we need to reach, and once we've reached there, we'll put it into the op-amp equation, which is
VO equals AV brackets V non-inverting minus V inverting.
yes, VR equals AV V plus minus V minus. Imprint it onto your brain next to Ohm's law and slightly above loop and node analysis. So we need VR is equal to AV V plus minus V minus. So this is, you've just got to remember this. If you don't like to remember, you can convince yourself how it comes about due to that in the prior lecture, not the last, but lecture 15, we were talking about feedback systems in general terms, and I had G was the forward gain, H was the feedback gain, all that sort of thing. That's how that drops out. If you need to be convinced more, there are lots of good control textbooks, but they probably won't help you that much because they don't really deal with the nitty-gritty of it. So I'd stick to something like Sedgwick and Smith or Horowitz and Hill. Of course, if you do go down Horowitz and Hill, you might come across op-amp man. But Horowitz and Hill's quite an old book now. I don't really like people inside op-amps because it's not, I don't think we have to do that. It's a little bit GCSE. So this, I'll call this equation 1 because I haven't labelled any others, and I'll call this 2. So 1 has to go into 2, which will get rid of the V minus and replace it with all this stuff. And the V plus goes away. Back here we had V plus was grounded. So then you put 0 in for V plus. Well, that's just disappointing. Anyway, that what goes in there, 0 goes in there, and what you end up with is V out equals stuff and things including V out. So you have to collect all the V outs together, and then divide that V out by any V ins that you've got, and then you get V out over V in equals resistors and algebra. If you want to see the last bit done, it is done in the lecture 16 slides, but I don't really think it's necessary to stand here and just do algebra. I don't think it helps very much. So, the reason I'm prepared to do the first bit is because it's involved with the circuit, but when it just becomes maths, there's no need to carry on. Well, not here anyway, obviously in the exam you have to carry on. So, what's the time? 1:30. Righto. Should we do this one then? Biscuits!
People don't get that, point of extra.
Right. So how do we proceed with this? Is obviously the non-inverting one, non-inverting amplifier. How do we proceed with it? Where do we begin? I'll quick rifle through the notes. What? Voltage across the resistors. Okay, so we have V in and V out. And we'll call this R1 and we'll call this R2. So what I really need to do is be able to get to a situation where I can use my V plus equals V minus, because this op-amp's got infinite open loop gain, or AV is infinite. So V plus equals V minus, and we need to be able to say something about V plus and V minus in order to equate them. So V plus equals VI. I don't think that really deserves a biscuit. I don't want to contribute to your diabetes. So first thing we have to say is oh no. Watch out, Chapman. Right. So V plus equals V in, and we need to say something about V minus as well.
V minus equals the potential division in V out with R and R2.
I didn't hear anything. Somebody say something? V minus is equal to V out times, this is going to be quite small actually. I'll do it down here instead. V out is equal to, V minus is equal to V out times R2 over R1 plus R2. So what we're saying there is that V out is potentially divided between R1 and R2 to yield the inverting input voltage. So we've got V plus and V minus, and we can say, well, because the gain of the op-amp is infinite, open loop gain, we will just set them equal to each other. So we'll have V out R2 over R1 plus R2 is equal to V in. If I just go V out over V in is R1 plus R2 over R2, is everybody cool with that? Or is that too much? Well, you're silent, so it's clearly too much. So we'll divide through by V in, and this has to go the other side because it needs to divide through. So we'll do V out is equal to VI divided by this lot. And then we'll divide through by V in, which will yield 1 there, and V in there, and that 1 over fraction just flips that bottom fraction. If you need to prove that to yourselves, it's really one for just before bed, I think. So that's how the non-inverting one's done. And there is a non-inverting one where the gain is not infinite, and you have to proceed along the same lines, with the exception that you cannot actually say, from this point where we've got the chalk on my face now, you cannot say that V plus equals V minus. You have to say V out is equal to AV, V plus minus V minus, and you sub in V plus is equal to VI, and V minus equals V out R2 over R1 plus R2, and then you rearrange it to get all of the outs together, divide by the VI, how many VIs you end up with, and you'll get an expression, and it's something along the lines, well anyway, it's in your notes. So the rest of it after that is just algebra. The key things are knowing that for the inverting amplifier, it's a virtual earth, and you sum the currents at the inverting node. To know that V plus equals V minus for an op-amp with an open loop gain of infinite, AV is infinite, and you can apply that expression to both the inverting and non-inverting versions. And to know that when the gain is not infinite, so AV is finite, you have to invoke the op-amp equation and the process of analysis to figure out what V plus is, figure out what V minus is in terms of V out and V in, and then substitute both of those into the op-amp equation and then rearrange for V out divided by V in usually. That's the key thing. The maths is just a little thing that gets in the way. Right. Oh, I've got to log in now, haven't I? Bugger it. Right, while that warms up, any questions about anything that I've done at all? Preferably don't say all of it, starting when? September. Anything on transistors that you're not happy about? Anything on diodes? Anybody still sad about that horrible 118 question that went around in the personal tutorials? That's been set every year since long before I was a student. Every year it kills everybody. But if you were to say to the person who wrote it, this is far too hard, what he'll say is, you should have seen the ones I got. So it's not going to go away. Luckily there isn't anything like that on the exam for 118, because it'd be a bit mean. I think in fact that particular problem sheet is a good example of why lots of people think analog is a bit of a dark art and they would prefer to leave it alone as fast as possible. It's not that it is difficult. I mean, this is the first time we've done any serious maths, really, other than a couple of loops. So it's all about figuring out what goes on in the circuits, and that means you have to know what to think, and the knowing what to think takes experience and practice. And that's why it appears difficult. If you can just write some equations and derive an answer, you can learn that mathematical process quite quickly, and you can memorise how you do it, and then everyone's the same. For analog problems, every time you get to it, you have to summon up all of your analog knowledge and figure out which bits are important for solving the particular problem you're up against. So every problem is like a new problem. So all you have is these tools in a sort of analog toolbox, and you have to get experienced at which tool is the right one for the job. And that's why I think people find it quite tricky. But obviously some people persevere, and it's quite lucky that not many do, because if you did get into analog as opposed to systems or test or VLSI or whatever, because there are so few people doing analog, obviously you get paid quite a lot. So it might be worth persevering for financial gain. No screen. I would have stopped then. No. Obviously the best reason to do anything is because you love it and you want to know the answer. And the next best thing is because you really like the teacher. And the next best thing after that, now you'll find this in books on educational theory, which I can give you a list of references if you wish. It's frozen, so I'll carry on for a bit. Second best reason because you like the teacher. Third best reason for financial gain. Fourth best reason because somebody like parents is making you. And that goes by motivation. Best kind of motivation is because you just need to know the answer. Worst kind of motivation is because you are threatened with disgrace or whatever if you... Well, a few years ago, somebody turned up and would not engage at all. And eventually I said to her, why are you even here? Well, I was a little bit tired by this point. This was about March time. And she said, Dad's making me. Right, what do you want to do? I want to be a diving instructor. And it turned out that Dad had an audio company and wanted daughter to become an engineer. And that wasn't happening. And obviously, oh come on. He should have got him to put some more RAM in while he was here. If he brought Robin as well, it'd have been alright. Oh, come on. Right, looks like we're off. I mean, you could think about engineering the same way you could think about learning, I don't know, learning to plaster walls or learning to play guitar or something. If you want to be in the fastest metal band in the world, you'll have to put in about 15,000 hours of just playing scales over and over and over until you are faster than everybody else. If you want to be really good at electronics, you'll have to do practice over and over and over until you're brilliant at it. There is not nearly as much kudos for being good at electronics as there is in being whatever silly band is currently the fastest. But this is where we are. So, summing amplifier. This is essentially an inverting amplifier in disguise, and the nature of the disguise is that there is more than one input resistor. That is all there is to it. So, knowing... Ooh, it's a biscuit. Knowing that for the case where AV is infinite, we know that V minus equals V plus, and that V plus is ground, and that's how the virtual earth is sustained, and so on. It is therefore fine to treat every one of the inputs as if all of the others don't exist, and then to add up their contributions afterwards. That is to say, we use superposition. So I would work out the gain from V out to V1, or V out over V1 is minus RF over R1. Happy with that? And I know that R2, R3 and Rn aren't going to come into it. If you wish, you can prove that to yourself. And the way that you would do it is you'd set V2, V3 and Vn to 0, and then you do all the maths as if they were all in there, and you'll find that because you've got V2, V3 and Vn at 0, all the terms with R2, R3 and Rn in disappear. And when we do superposition, that's really what we're saying. What we're saying is they're all voltage sources. And if we do superposition of 4 voltage sources, we'll select the first one and turn it on, and we'll switch off the other 3, and we'll replace them with their internal impedance. This is before Christmas stuff. And that will be 0 ohms because they'll be perfect sources, so they'll all be connected to ground, so they'll be 0. Happy? The only thing that's scary is the circuit's a bit bigger. This circuit will not come up with AV is not infinite, because it's a little bit mean, and the equations are quite large. There's no more difficulty involved, it's just you only have a certain amount of time to answer a certain number of questions, and I'm not designing a test which tests your ability to derive big equations. So this is the sort of thing you find in an audio mixer, for example, if you wanted, I don't know, guitarists too loud, louder than the other three guitarists, and you want to turn them down a bit. You could adjust the values of RF and R1 compared to R2 and R3 and Rn to dial it back a bit. The derivation I will leave to you, but it's essentially you do the same derivation as inverting input, one inverting input amplifier, but then you say, well, I can use superposition on this. So what happens if we've got more than one input going to both types, or at least one input going into both inverting and non-inverting? Well, we end up with a subtractor. For this one, you can derive it if you wish, but the method is the same. Essentially, you've got to work out what V minus is, and you do that by saying there's a current IF and a current I1 in this case, and you set them equal to each other because you say the gain is infinite, so there's no current going into the V minus terminal. As a consequence of that, you derive the usual maths, and that's the same maths as for the inverting amplifier. And then you'd say, well, V plus is V1 potentially divided between R2 and R1. So you've got an equation for V plus in terms of V1. And then you'd say V plus equals V minus, smoosh it all together, and finish the job. And do I do it? I did do it. You end up with V out is R2 over R1, V1 minus V2. Essentially, it subtracts the non-inverting input driving voltage from the inverting input driving voltage. And if you choose R2 to be equal to each other and R1 to be equal to each other in the diagram that's shown, you end up with a subtractor with a gain of R2 over R1. There is nothing to stop you making those resistors R1 through R4 and picking different values for each of them. And there will be certain situations where that is something that might be desirable. But it depends on the application, and the usual way you'll find it in a textbook is drawn out like this, where R2 and R1 are equal but different from each other. So there's two R1s and two R2s, and the R2s are equal, and the R1s are equal, but R1 is not equal to R2. Yeah? Nah. Right, so there's some maths, which you can do at home. What if we had a general multiple input circuit? There is actually an even more general one than this. I could, if I so desired, put an R4 in here. Oh no, there's an R5. An R5 in here, and a V4, and hook it up to there. And then I have two inputs on the inverting side and two inputs on the non-inverting side. Might be nice to practice a question like that. We still do it by superposition though. And you still do the same things you usually do. You'd say, well, V out to V1 is an inverting amplifier where the gain is minus RF over R. And V out to... Oh, there's a mistake, isn't there? Sorry. That should be R2. Somebody drop me an email to remind me. Otherwise I won't change it. So yeah, second one down is R2. So for V2, you'd have V out over V2 is minus RF over R2. And for V out over V3, you'd have RF over R1 parallel R1, because they're both written as R1, times R4 over R3 plus R4. And the reason is, if I drive this, I'm going to have to ground these two because I'm saying that they're not involved. And if I'm doing it by superposition, which I am, they have to be replaced by their voltage source internal resistance, which is 0. So now I've got a non-inverting amplifier because I'm driving the non-inverting input, and my gain setting resistors are this one, because it goes from output to inverting node, and these two in parallel, because they're both connected to ground and they're both connected to inverting input node. These two resistors are an extra feature, and all they do is make the input voltage look slightly smaller in the ratio of R4 to R3 plus R4, because it's just a potential divider. I suspect that's on the next slide. It is. So if you didn't catch that, consider the first output due to V1. V2 and V3 and V4 are all grounded, so they've been replaced by their internal resistance. And the circuit's just an inverting amplifier, so we get minus RF over R1. So when I write like this, it's VR due to V1. That's how you would read it. And that turns up all over the place in mathematics. So then we could say, well, by changing the variable names, we can do V out due to V2, and I did put R2 here, so I didn't carry the mistake on. So that's fine, that's just inverting as well. And then the output due to V3 is a bit more complicated. And the derivation is there, so we do V out over V plus first, so that's the non-inverting amplifier bit, and we'll end up with RF plus the total to ground, which is R1 parallel R2, divided by the total to ground, which is R1 parallel R2. But then we have to do V out, another mistake. V plus, just there. It's clearly getting a bit tired of writing lecture notes by this point. Although that doesn't explain any of the other mistakes. So we've got V plus over V3 is R4 upon R3 plus R4, which is just the potential divider of these two. And you squish those together into 32 and then rearrange it to get 33. And then the same arguments can be given for V4 as well. And then you just sum up the totals, so you do V out due to V1 plus V out due to V2 plus V out due to V3 plus V out due to V4, all equals V total. Is there actually a V4? There isn't. Oh, there's a V4 down the bottom. So this isn't grounded, I've snuck in an extra voltage. What a bastard. There's no reason why I couldn't make that -5 if I wanted to, in which case it would adjust the way this potential divider worked a bit, because the potential would be divided between V3 and V4 across these two. So, if any of these inputs have an AC and a DC component, you can treat them separately. That's to say, if I had, let's just imagine V1 was 5 plus 10 sine omega t minus pi over 2. So it'd have 5 volts DC, 10 volts peak AC, sine wave, at a frequency omega that I didn't specify, with a phase shift backwards of pi over 2 radians. And you could say, if I'm worried about DC, I'll ignore all that stuff and talk about the 5 volts. And if I'm worried about the AC, I'll get rid of the 5 volts and talk about the 10 sine omega, whatever the hell I said. And you can do that for all the inputs. Although if I wrote a question where every single input had a DC and an AC component, that would be a bit mean. So they don't usually come up. If you want to see what kind of questions usually turn up for, there's always an op-amp question, always. So if you want to have a look in past papers, you'll be able to see the thread of it. But usually, there's some simple stuff, like draw an op-amp. There's some slightly harder stuff, like assuming, yeah, you've got a mark there. Assuming the gain is infinite, derive a circuit. It's only really 2 choices. And then there'll be another question, another part of the question, which will be some multiple input thing. Sorry? It's not switched on. But I don't want it switched on. I'm afraid it's not me.
Is it map mentioned as 6? So, you didn't call, right?
No, I called earlier, but you...
Yeah, yeah.
Yeah, sorry. Righty. So there's a bit of a review. We're out of time. And that's the notes for the resources. If you haven't seen them, then God save you, because it contains everything. And there's the back.